All right, let's dive right into a clinical scenario that is, well, as common as it is dangerous. We're going to use this really powerful 5-step method to decode the arterial blood gas, or ABG, and uncover some life-threatening problems that might just be hiding in plain sight.
Let's start with a bit of a puzzle. Have you ever had that moment where you look at a lab value, it looks perfectly normal, and you breathe a sigh of relief, only to realize later that the patient was actually in the middle of a severe metabolic crisis? What if that normal number was actually a trap?
So, take a look at these labs for patient 2. The pH is kind of borderline, sure, but the bicarb is 25, and look at this, the base excess is plus 0.6. I mean, on the surface, that looks totally fine, right? Reassuring even.
But what if I told you that this seemingly normal number is actually the result of two powerful opposing forces just canceling each other out? What if this picture of stability is actually just a dangerously deceptive illusion?
To figure out what's really going on, we need a tool that lets us pop the hood and look at the engine, so to speak, of that single base excess number. And that tool is a simplified, really practical approach called the Stewart light method.
And don't worry, this isn't about some dense, complicated theory. It's a practical 5-step algorithm and lets us systematically break down the base excess into its core components so we can see all the individual forces at play.
Okay, so before we solve the mystery with patient 2, let's build up some confidence. We're going to walk through these 5 steps with a much more straightforward case, just so we can see exactly how this method works in action.
So, here's our first patient. They're in septic shock. Their ABG shows a severe metabolic acidosis, and you can see that reflected right here in their standard base excess, or SBE, of -12, and that is a big, scary number. Okay, so let's get into it. That -12, it tells us that there's a problem, for sure. But it doesn't tell us what the problem is. Is it lactate? Is it something to do with their chlorides? Is it something else entirely? Let's use our method and find out. Step 2 is where we figure out the impact of what we call the strong ions. This formula, it basically just looks at the relationship between sodium and chloride. They're the two most powerful electrolytes that influence our acid-base balance.
Okay, let's plug in the numbers for our patient. You can see their sodium's 140, their chloride is 110. So, we take 140, we subtract 110, then subtract that constant, 35, and that gives us -5. So the key point here is that this ion imbalance is contributing exactly -5 millimoles per liter of acid to the patient's overall problem. Now let's move on to step 3, which accounts for albumin. Now this one is a little counterintuitive, so stick with me. Because albumin is a weak acid, when you have a low level of it, it actually has an alkalinizing effect on the blood. Kind of weird, right? Now this is where it gets really interesting. Our patient's albumin is low, it's at 20. So let's do the math. 40 minus that 20 gives us 20. Then we multiply by 0.3, and that equals +6. This means their low albumin is actually acting as a base, and it's hiding a full 6 millimoles of acid that we would have completely missed otherwise. All right, on to step 4. See how this is all building on itself? This is where we find the hidden stuff, the unmeasured ions, like lactate or ketones. It's simple. We just take the total SBE and subtract the two pieces we just calculated. Okay, let's put all the puzzle pieces together. We start with the total SBE of -12. From that, we subtract the strong ion effect, which was -5. Remember, subtracting a negative is like adding. Then we subtract the albumin effect, which was +6. And the result? We've just discovered a hidden -13 millimoles per liter of unexplained acid that's coming from these unmeasured ions. And boom! Check this out. This chart just lays it all out perfectly. You can see how the -5 from the strong ions, the +6 from the albumin, and that big -13 from the unmeasured ions all combine to create that total SBE of -12. We've totally broken down the problem. Okay, so we've got the hang of this tool, right? We know how to break down the base excess. Now let's get back to our original mystery, patient 2 and their deceptively normal blood gas.
We're going to run the exact same 5-step process, but this time on those numbers that looked so harmless at the start. The truth isn't in the total, it's in the components.
So let's do it again. Patient 2's sodium is 128. We subtract their chloride of 98, and then we subtract our constant of 35. That calculation reveals a strong ion acidosis of -5. That's a pretty powerful acidifying force hiding right under the surface. But at the exact same time, look what's happening with their albumin. It's low at 25. Let's do the math again. 40 minus 25 gives us 15. Multiply that by 0.3, and we find a powerful alkalizing effect of positive 4.5. Are you seeing what's happening here?
And here it is. This is the reveal. This is the whole trap. You have an acidifying effect of -5 and an alkalizing effect of plus 4.5, and they are almost perfectly canceling each other out. It's a metabolic tug-of-war. And this cancellation, this is what results in that final, misleadingly normal base excess of plus 0.6. It was hiding a severe mixed metabolic disorder, a big, strong ion acidosis completely masked by a big hypoalbuminemic alkalosis.
So what's the big takeaway here? What's the crucial thing to remember from all this for your own clinical practice? Why does this even matter?
Here's the key lesson. You absolutely cannot stop at that single number on the lab report. A normal base excess does not mean there's no problem. It could mean there are two huge problems fighting each other to a standstill.
So the next time you have an ABG in front of you, just remember this case. Go beyond that single number. Check the ions, check the albumin, and find what's hiding. Using this simple method empowers you to uncover the complex reality and truly understand what's happening with your patient.